In the previous video, we learned about Gaussian elimination. In this video, we will learn another method in solving systems of linear equations called the Gauss-Jordan elimination. First, we will define a matrix that is in reduced row echelon form or in RREF. A matrix is said to be in RREF if the following conditions are satisfied. First, the matrix must be in REF or in row echelon form. We defined REF in the previous video. A matrix is in REF if the following conditions are satisfied. The first non-zero number in each row must be 1, and we call that the leading entry. The leading entry in each row is to the right of the leading entry in the row immediately above it. And lastly, if there is a row with entirely of zeros, that row must be in the most bottom part of the matrix. The second condition is that every number above and below each leading entry is a zero. For example, this matrix, as you have observed, is in REF. The first non-zero number in every row is a 1. This matrix is in reduced row echelon form or in RREF. This matrix is in REF, and the entries above and below every leading entry is a 0. For this leading entry, the entries below this number or this entry are 0. For this leading entry, the entry above and below it are 0. For this entry, the entries above it are 0. How do we transform a matrix into RREF? We can do any of the following elementary row operations. We can multiply k to a row and add that to r sub I, the ith row. We can multiply a constant k to the ith row. And lastly, we can interchange the ith and the jth rows. So here is a systematic way to put a matrix in RREF. First, we put the matrix in REF. And how do we do that? We discussed this in the previous video. We first start by obtaining a 1 in the top left corner and then obtain zeros below that 1. How do we obtain zeros below that 1? We simply multiply the first row with the appropriate constant and add that to the rows below it. Next, we obtain a leading entry 1 in the next row and then obtain zeros below that 1. We continue this process until we arrive at a matrix that is in REF. Number 2, we obtain zeros above each leading entry with the same strategy that has been mentioned a while ago. We multiply a constant to the leading or the row containing the leading entry to the rows above it. And in other words, we start at the most bottom row and work upwards. So if we solve a system of linear equations using the RREF, then we call this method the Gauss-Jordan elimination. So how we do Gauss-Jordan elimination? We first transform or express the system in augmented matrix. Next, we transform the augmented matrix in RREF. And finally, we write the new system of equations that corresponds to the RREF of the augmented matrix. Example, let us solve the following system of linear equations using the Gauss-Jordan elimination. Going back, we first express the matrix, or we write first the system in augmented matrix. So to do that, we start with the first row. So the coefficients of the matrix or the coefficients of the equation are 4 8, negative 4, and the constant is 4. For the second row, we have 3, 8, 5, negative 11. For the last row, we have negative 2, 1, 12, and the constant is negative 17. Then after that, we transform this matrix in row echelon form. So we begin at the top left entry. We want to make this entry or 1. So to do that, we multiply the first row by 1/4. So we will get here, we simply copy the second and the third rows. And the first row is transformed into 1. 1/4 times 8 is 2. Negative 4 times 1/4 is negative 1. And 4 times 1/4 is 1. After that, our strategy is to obtain zeros immediately before the leading entry 1. And how do we do that? We multiply appropriate constants to the first row and add that to the rows below it. So for the second row, I will multiply by negative 3 to row 1 and add that to row 2. Why will I do that? So that I will get a 0 here. Let's see. So I will simply copy the first row and the second row is transformed into negative 3 times 1 is negative 3 plus 3 is a 0. Negative 3 times 2 is negative 6 plus 8 is 2. Negative 3 times negative 1 is positive 3 plus 5 is 8. Negative 3 times 1 is negative 3 plus negative 11 is negative 14. Now for the third row, for this entry, I need to obtain a 0 here. So what I can do is I will use row 1, this 1 here, I will multiply that by positive 2 and add the first row to R3. So I will get here 2 times 1 is 2 plus negative 2 is a 0. And that's our goal. Then I have 2 times 2 is 4 plus 1 is 5. 2 times negative 1 is negative 2 plus 12 is 10. 2 times 1 is 2 times negative 7 plus negative 17 is negative 15. That's it. And after that, we need to obtain a 1 here. How do I do that? I will multiply the second row by 1/2. In doing that, I simply have to copy the first and the third row. No changes for the first and the third row. The second row now becomes 1/2 times 0. I'll get a 0 here. 1/2 times 2 is 1. 1/2 times 8 is 4. 1/2 times negative 14 is negative 7. After that, I need to obtain a 0 below this leading entry. And according to our process, what I can do is I will use this 1 here. I will multiply here an appropriate constant and add that to row 3. So in this case, I will multiply this by negative 5 and add that to row 3. So first, I will copy the first and the second rows. For the first entry, I have negative 5 times 0 is 0 plus 0 is a 0. Negative 5 times 1 is negative 5 plus 5 is a 0. Negative 5 times 4 is negative 20 plus 10 is negative 10. Negative 5 times negative 7 is positive 35 plus negative 15 is positive 20. Next, I have to obtain a 1 here. So I will have a leading entry that is a 1 for the third row. So to do that, I will multiply row 3 by negative 1/10. So copying the first and the second rows, I have here a 0, 0, and positive 1 and negative 2. This matrix is already in REF, but for Gauss-Jordan elimination, I must transform the matrix into RREF, meaning I have to obtain zeros above this leading entry. So how do I do that? I will multiply appropriate constants to this one and add that to these rows. So for row 1, I need to make this a 0. So to do that, I will add row 3 and row 1. So I will first copy the last row, and row 1 becomes 0 plus 1, 1. 0 plus 2 is 2. And then 1 plus negative 1 is a 0. That's our goal. And then negative 2 plus 1 is negative 1. Next, I have to obtain a 0 here. So to do that, I will multiply row 3 by negative 4 and add that to row 2. So I will have 0 plus 0. Negative 4 times 0 is 0 plus 1 is a 1. Negative 4 times 1 plus 4 is 0. Negative 4 times negative 2 is positive 8 plus negative 7 is positive 1. So as you can see, we have already obtained zeros above this leading entry. Now our next goal is to get a 0 here. The entry above this leading entry. So to do that, what I can do is multiply row 2 by negative 2 and add that to row 1. So let me copy the first and the second rows. No, sorry, the second and the third rows. I will simply copy them and multiply negative 2 here. So I have a 0 plus 1 is a 1. Negative 2 times 1 is negative 2 plus 2 is 0. Negative 2 times 0 is 0 plus 0 is 0. Negative 2 times 1 is negative 2 plus negative 1 is negative 3. Now, as you can see, this matrix is already in RREF. This matrix is in row echelon form, and the entries above and below every leading entry are all 0. So this is in RREF. Now writing, for the last step, we have to express this in systems of linear equations. So for the first equation, I have this column is x equal to negative 3. This column is for variable y, so I have y equal to 1. And lastly, this column is for variable z equal to negative 2. So we already have solved the equation. The solution is the point negative 3, 1, negative 2.